Good morning and welcome back. We will now begin today's first session entitled CDR and Utilization. First of all, I would like to introduce our moderators and speakers for this session. For our moderators, Professor Sally Ann Benson, ICEF Steering Committee, Professor, Energy Science and Engineering, Stanford University, Deputy Director for Energy and Chief Strategist for the Energy Transition, White House Office of Science and Technology Policy, United States of America. Mr. Vikram Singh Meeda, ICEF Steering Committee, Chairman, Center for Social and Economic Progress, Research Foundation, India. And for our speakers, we have Dr. YOGO Katsunori, Group Leader and Principal Research Scientist, Chemical Research Group, Research Institute of Innovative Technology for the Earth, Japan. Mr. Marcus Dove, Founder and CEO, MCI Carbon, Australia. Professor Sugiyama Masakazu, Director and Professor, Research Center for Advanced Science and Technology, the University of Tokyo, Japan. And Dr. Roger Deane Aines from Livermore, United States. And I would like to ask our main moderator, Professor Benson, to moderate this session. So Professor Benson, please take the floor.
Thank you very much, and good morning to everybody. Thank you for joining us for this very important discussion about carbon dioxide removal and utilization, which are key strategies for the collective effort around the world to reach net zero emissions and beyond. The IPCC Sixth Assessment Report concluded that carbon dioxide removal, or CDR, will be necessary to achieve net zero emissions. Before we jump into the topic, I want to say a little bit about what is CDR, or carbon dioxide removal. In fact, it's an umbrella term for many different types of technologies, BECCS, bioenergy plus carbon capture and storage, bikers, biological carbon removal, direct air capture, mineralization, marine carbon removal, so very many things. So it's very, very broad. And this session is going to deal with the particular topic of what to do with the carbon dioxide after you have taken it from the atmosphere. So how do you get it out of the atmosphere, and what do you do with it? And there are two major strategies for what you do with the carbon dioxide you've taken from the air. One is you permanently sequester it in deep geological formations or possibly in minerals. The second one is that you utilize it. And part of the thinking behind this is if you've gone to all the trouble to remove the carbon dioxide from the atmosphere, spent a lot of money and so forth, wouldn't it be nice if we could use it to make valuable commodities which could then be sold to create a carbon neutral or a carbon negative economy? So that's what we're going to talk about. So the current target, as indicated from many modeling studies, is that we're going to need about 7 to 9 billion tons of CO2 a year, of CDR, by 2050. And if we look at today, we're removing about 2 billion tons per year, and it's mostly through forestry. Or nature-based solutions. And one of the challenges of that is that it really isn't permanent, and particularly it can be taken back, for example, by wildfires, which have grown prevalent in many parts of the world. So we have this huge scale-up needed, which really speaks to the urgent need and imperative for innovations in these technologies. So the session today is going to focus on the current landscape, covering some of the technical developments, not all, but some very important ones, innovation, demonstration projects that are taking place, and then, of course, the challenges, because these are very early days. We'll also talk about the role and benefits and drawbacks of CDR and utilization compared to direct reduction of emissions. And we'll explore the balance between these two critical approaches for getting to net zero targets. So the session will, as you heard, will be moderated by myself and Mr. Mehta here. And we're very pleased to host our distinguished panel that you have already been introduced to by our host. So I think we're just going to jump right into this, and we will go through each one of you, and you will make some remarks, and then we will have a general set of discussions with the moderators and the panelists, and then we will open it up to the audience. So please do think of your questions, so when we come to that part of the program that you'll be ready with some interesting questions for our panelists. So Professor YOGO, let's please get started.
Okay, thank you very much. And I'm YOGO from RITE, Chemical Research Group. And it's my great opportunity to have a chance to introduce our research activities. So, this. Okay. For over 20 years, RITE has been developing various CO2 capture technologies and membrane separation for high-pressure gas stream and CO2 capture from a hydrogen production process. And chemical absorbent solution developed by RITE are already in practical use. And currently, 2 commercial facilities are in operation in Japan. And solid solvent methods are being developed for thermal power plants and DAC. And RITE is exhibiting a DAC pilot scale demonstration plant at the Osaka Kansai Expo. And DAC demonstration tests are being carried out as a part of NEDO's Moonshot type R&D project. RITE developed amine for DAC, and Mitsubishi Heavy Industries Group designed and manufactures the equipment. And it employs the steam-aided vacuum single absorption method, where the low temperature steam at 60 degrees C is supplied to the saturated materials to raise the temperature and concentrate the CO2 over 95%. And compared with the overseas, it is small, but this is the largest test facilities in Japan. And that is the 300 kilograms per day equivalent. The CO2 captured by DAC is supplied for a variety of uses. And Osaka gas for methanation and use it for in cooking at the guest house. And air water for produces dry ice. And also Mitsubishi Gas Chemical Company for methanol synthesis. For Osaka gas and air water is a neighboring site of our facilities, but Mitsubishi Gas Chemical Company is located in the outside the expo site. And this summarizes challenges for scaling up and social implementation. And advantage of the RITE DAC, our DAC, is the low temperature regenerative, highly oxidative degradation resistant light amine solid absorbent system. And we use the 60 degrees low temperature steam and high equipment and system reliability that is manufactured by Mitsubishi Heavy Industries Group. So to date, there is almost no machine trouble through the XP period. And we are currently experiencing the learning by doing through large-scale demonstration. And we found several challenges. And we will improve them. And most important point is we found that the most important point is mitigating the impact of the humidity. And we plan to continue improve the materials and the systems. And to achieve the widespread absorption of dark is I show here, and time is finished, so I finish my presentation. Thank you for your attention.
Hello and welcome. My name is Marcus Dawe. I'm the CEO and co-founder of MCI Carbon. We're an Australian company. Slides, please. We're an Australian carbon technology company. We've been going for 13 years and developing technologies in this field to turn CO2 into materials is a 20-year journey. Most technologies that you see in industry have taken that amount of time, and so the journey has been a long one for us, but it's methodical and we're moving towards industrial scale. And I'm going to take you through that journey a little bit here. We've received many millions of dollars of research and development support from our Australian governments continuously for 13 years. This is really important in developing technologies like ours. What we do is we turn CO2 and minerals or wastes into materials that can be used in the circular economy. And this is really, really important because it means we can permanently store away CO2 but create value as well. And pathways that can create value are the ones that are going to succeed more early and ostensibly to scale, which is really important. In the COP26 in Glasgow, we were named the #1 clean technology in the world, which is a very big accolade for us, and it's accelerated our activities towards getting funding for our technology. Importantly, what we do is we transform that CO2 using a chemical engineering process into different types of materials, mainly for construction, but also in the building environments. So this is concrete, drywall, refractories, paint, paper, glass, many other types of materials. When you think about how we construct and we manufacture materials right now in our world, we have to use carbon-embodied materials or low-carbon materials, and that's what we're focused on. So importantly, we can take CO2 from any source. So CDR is really important for us. But at the moment, we take it from industrial sources where we can capture it straight from flue gases, for example, which is really, really important. So the pathway for us is to take the CO2 from wherever we can get it, and then to in the longer term, take it from those processes like DAC and also BECCS and others that can provide us with that pathway. This is Myrtle. This is our TRL Level 7 plant that we're about to turn on next month in Australia. And importantly, this will transform and create about 3,000 tonnes of carbon-embodied materials, which including a low carbon and a carbon neutral concrete. In Japan, we're already in operation. We're working with Itochu Corporation, but also our investors with Mizuho Bank, Sumitomo Mitsui Trust Bank. We also have just signed an agreement with the second largest cement maker in Japan, which is Mitsubishi Ube Cement Corporation. It's very, very important that we can help decarbonise our economies as quickly as possible by using CO2 as a feedstock. Thank you very much.
Okay. So it's my turn. Good morning, everyone. I'm SUGIYAMA, University of Tokyo. I myself is enrolling in a lot of the research activities and also some advocacies related to all the aspects of the carbon neutrality target. And today, my topic is focused on the CCU utilization. Since as is here, my interest as the CCU is targeted at the chemicals, right? Even though we achieve carbon neutrality, we have definitely demand for the chemical product, which includes carbon. So the question might be, where is the source of that carbon? That should be the CO2 in the atmosphere. That's a very simple question and answer. So for that scheme, we need to definitely achieve some form of the CCU to produce the chemical feedstocks. And our focus is ethylene, which is the most widely used chemical feedstock. And we actually have lots of the applications and also the cases for the implementation. And as in my moonshot project, since our leader is asking us to present some new application, so my proposal here is the converting this skyscraper building to the site of the artificial photosynthesis, in which we can collect CO2 from your breathing air or from the outside air to the collected CO2. Because in this particular building, we have an air ventilation system where we already have a very nice airflow. So if we implement a distributed, small-scale, implementable carbon capture system into that air ventilation duct, for example, then we should be able to collect all the CO2 related to your emission and also related emission from the atmosphere. So the next question might be how to combat that CO2 to the chemical feedstocks. Yes, we can transfer our captured CO2 from this building to some chemical plant, but we may provide you some alternative, which is actually distributed a CO2 conversion system to our chemical feedstocks, such as ethylene. So how that should look like? So we are targeting at implementing such kind of very compact modular system to hopefully some utility area of individual buildings. You go to this basement, then you will see already some air ventilation, air cooling, heating, all the utility systems, which actually has a substantial space. So we're gonna implement 2 electrochemical systems. After the CO2 capture, we will first implement the electrochemical system of the purifying the CO2 from some percentage, some couple percent scale concentration to 100% CO2. And the next one might be the conversion of that captured and condensed CO2 to our chemical feedstock ethylene. And that is the electrochemical system. Imagine your fuel cell, your water electrolyzer, your battery cell. All of these devices are electrochemical, and these are modular. So if we make a good effort to implement such electrochemically based CO2 utilization system, it should be possible, not only such a gigantic scale plant, but also using this kind of the building to be a site of the artificial photosynthesis. This is my target and also the near future dream. Thank you so much.
Thank you. I'm Roger Aines, and I've worked in CDR for 15 years. We developed a program at my laboratory in Livermore to understand what CDR is and how it could be applied. And in the last 2 years of the last administration in the United States, I was the advisor to the government on carbon dioxide removal. This has given me a very broad view into what we need to do to move forward in this area, and I want to talk briefly about that. ICEF is anchored in innovation, the first step. And CDR has gone through an amazing innovation phase in the last 10 years. When we counted last January, there were 790 companies around the world pursuing CDR and representing almost that many technology variations. New innovation is still important, but it's going to be dwarfed by the next phase for those companies. And that next phase is not growth. It's acceptability. We have to show that people accept these technologies because they work and because they're comfortable having them in their communities. This is like cell phones in 1980. We had to be convinced that this was a good idea. Once we were convinced, the world changed very quickly. But that's where we are with CDR today. The money appeared for cell phones once the investors saw the reduced risk. We all keep thinking about what we need in 2050, and that's what all the models point us at. But I like to think about what we need next week and next year in order to keep these things moving. These technologies are currently very expensive, but there are buyers. 38 million tons of removals are under contract today for a total of $10 billion. Yes, that's an average of $250 a ton. And all of that's happened in just 3 years. That's a very rapid growth in that field. 40 companies have purchased more than 10,000 tons in the private market. And why are they buying them? They want to know if CDR meets their needs. They're trying it out. They're testing the acceptability of CDR. They're investing in CDR. That's most important. And Today, the methods with established supply chains are the ones that are selling the most removals. It's supply chains that are the most difficult thing to put together today. Most of those big removals use biomass and store the carbon permanently in the earth. So the private market would like to buy more than they are. They would like the market to be bigger. But the limitation is basically these supply chains and that the companies have demonstrated that these things actually work before large companies are going to spend enormous amounts of money to buy these removals. And anyone will tell you that those costs must come down. History shows that cost reductions come from increased usage, which the private market is supporting today, thank goodness. But supply chains are really the challenge, and the individual companies don't have control of that. Fortunately, though, each one of those 790 companies has a slightly different supply chain. Marcus has a slightly different supply chain than every other person in that field. And this heterogeneity in the CDR market is its greatest strength, because each technology and each approach can find its Goldilocks location. From biomass in Northern Europe to geothermal in Iceland and Kenya, the resources are there to prove acceptability. The final comment I want to leave you with is that CDR does not have to displace any other industry. It can expand as fast as the resources and the acceptability permit it to. The customers have to find it to be acceptable. And that's the challenge today, to show that it works and that we like it. Thank you.
Well, thank you very much for that fantastic introduction to this panel discussion. So we're going to now ask you a set of questions, and we would like to start with Professor YOGO and Dr. Aines. And if others of you feel compelled to say an answer, please go ahead. But you know, we've heard about demonstration projects going on, and that's fantastic. It means that the technology is available, may not be perfect yet. But the reality is we need, as we heard in the beginning, to get to gigatons per year scale. So could you say a little bit more about your technologies, in particular about what will it take from a technical perspective, as well as from an economic perspective, to get to the gigaton per year scale? And how long might that take us?
Okay, thank you for your question. And from an economic perspective, the current cost of DAG estimated to be $300 to $600 per ton of carbon dioxide is too expensive. So we have to reduce the cost by at least half. And so therefore, the technological innovation is needed to reduce the cost. And to do this, the system must be simple and scalable. And the CDR and the characteristics of the CDR technology is a significantly larger production volume than the typical chemical industry. And our process uses amines and honeycomb-like supports. And it's a very good opportunity to adapt the well-established large-scale industrial technologies to CDR. And automotive use honeycomb for DAG. This is advantageous for the scaling up. And one of the biggest technological challenges of DAG is, for the material, is reducing the significant impact of water vapor on the energy consumption of the system. This applies not only to solid solvent system, but also to scrubbing solvent process, I think. Unlike the post-combustion capture, the air temperature and humidity fluctuate depending on the weather and the season. So I am a researcher in materials development. So I think it's important to develop innovative solvent materials. As you know, Mitsubishi Heavy Industries is one of the leading companies of this area and holds 70% of global share in the point source of capture, largely due to depending on high performance amines. And they said that the high-performance material enable the high-performance systems. So I want to say that the most important point that is to develop innovative solvent materials, particularly high durability and low humidity impact. And now it's in progress in our research group. I hope this answers your question.
Okay, thank you. Yeah, in terms of the energy, you already have a big advantage in that it's a relatively low temperature process. So, but it still seems like humidity management is still a significant issue. So thank you for highlighting that. Yeah, Dr. Aines, would you like to? You talked about supply chains being a big challenge. You talked about voluntary markets, you know, being eager for more of these technologies. But the voluntary market is likely to be only so deep. And yeah, what other approaches might we pursue to get to the gigaton a year scale?
Well, one of the things that we have to think about is if companies are going to pay a lot of money for this, and that's the lesson from the voluntary market, is that this is a valuable product, much more valuable than we imagined in its early days, and the price, of course, has to come down. But the important question today is that service actually being delivered? And this reflects in something called monitoring, reporting, and verification. This is one of the most important challenges we have today. Did this carbon actually get removed from the atmosphere? And this is becoming interesting for countries like Japan and Germany, where the service may be purchased from another country. And Article 6 of the Paris Agreement allows for this, and the 6.2, which is basically a bilateral agreement between two countries, is now in force, and 6.4, which is a general trading scheme, is close to being in force. And so it's today, what's going to happen is that there will be money moving around the world in order to perform the service, and that's going to require that we have a harmonized way of determining what you're paying for. Making sure that those tons are actually removed and that they count. And this is something that we've focused on in my laboratory, and we think about something called the net flux framework. And I want to be a little provocative here. The net flux framework says that if it didn't reduce the amount of CO2 in the air, it's not CDR. Think about that. It can still be mitigation. It can still be very important to do, but carbon dioxide removal has to reduce the amount of CO2 in the air. And so that's a thing that I think we all need to focus on, and there's going to be an enormous amount of discussion, because as large amounts of money start moving around the world, we need to agree with this. And one of the things I like to say is that the criminals are coming. There will be people who try to cheat on this, and we all need to be very careful and make sure that what we're doing is really cleaning up the air.
Michael, I enjoyed your presentation. My background is in economics, so I couldn't help but to reflect on the economics of what you have done. You mentioned that your whole process has a very long lead time, 20 years, and you are currently drawing your CO2 from industrial sources. But the thought was that if you were to actually draw CO2 from the atmosphere, it would be significantly more costly. I guess economists call it the green premium. So the question that I wanted to ask you is, how low does the green premium have to be for this whole technology, this umbrella of technologies, particularly CDR from the atmosphere, to be scalable and to be widely adopted?
Yeah, thank you, Vikram. Good question. So we operate, MCI operates on the principle that we're trying to get as economical as soon as possible. The green premium for us is around direct air capture integrations and things like that, which are very high in cost at the moment. If they can come down to $100 a tonne for capture, for example, we have our processes to the extent that we can make money from, like good money, from creating new materials. Really at the margin without a carbon price being significant. So if you consider that DAC and other capture technologies from CDR will integrate to us, we really want to see these technologies emerge quickly and drive down that cost curve. So we're driving the cost curves down with capture from industry, And that's the pathway then to when DAC and CDRs can become economical. So we think that, stop the emissions now and then remove the emissions as soon as possible as well. So we're hoping to be that storage or that the end state of permanent durable carbon can be, so that when these technologies emerge at economical stages and they need further funding, it's all about funding. The advantage is that CDR credits on the voluntary market are higher, so they are stimulating the technology developments, and that's what we need governments to do. But I'm very excited that these technologies are accelerating, but we do need the courage of governments to basically underpin their early stage developments, do the moonshots, and accelerate these technologies. I'm confident about that, but we do need the permanent storage.
So, this question is a follow-up to your answer, but it could, may I address it to all four of you, is that to what extent do you think that the CDR utilization would be implemented in preference to technologies that directly reduce CO2? Is that something maybe all four of you could address? Mike, you start. Yeah, all four of you, if you can just.
And I think that, of course, the technologies that directly reduce carbon dioxide emissions are more important, I think. And I think the first priority is promoting the electrification and introducing energy-saving technologies to reduce electricity demand and renewable energy and nuclear power, and next, hydrogen and ammonia. But if we can follow the LED scenario, low energy demand scenario, the CDR usage will be minimal. So, but however, in reality, the CO2 emissions are increasing year by year. According to the IEA, 7.6 gigatons of carbon dioxide will be captured in 2050, and of which 1 gigaton will be DAC. So and in addition, the researchers conducting scenario analysis says that for achieving carbon neutrality in 2050, there is no solution without CDR. So the CCS from large point sources and the CDRs are absolutely necessary to achieve carbon neutrality. So therefore, it is necessary to introduce CDR and the utilization technology as soon as possible and gradually increase it towards 2050. But we have to remember the DAC with geological storage. DAC is a backstop technology which determines the upper limit of the cost of the global warming mitigation technology and should be used to reduce the residual emissions from hard to abate sectors.
One concept I'd just like to play here is that the type of carbon credit created by durable, permanent, long-term storage from CDR will be in the future more valuable than any other type of carbon credit. That's something that I think Roger, many of us who are thinking long-term know will become the case, because it is extremely important that we do carbon drawdown. We need to draw it out of the atmosphere. We're going to overshoot our targets. Remember what Paris, what the Accord came together with, and that was we asked everyone what they want, and no one could agree on a global carbon price. So the next best thing was what don't we want, and that is more than 1.5 degrees of warming, which we seem we will overshoot. And all the IPCC targets, the next report will come out and highlight that we need carbon dioxide removal. So it's really the courage of the world, the government's regulation, and interoperability between the carbon prices of the world and different types of carbon credits are required that will drive the CDR revolution.
So I'm optimist. So my answer is very simple. The economy will follow us if we focus on the definite, regulation criteria. So if we first prioritize the carbon neutrality or net zero, then the economy may change if there is no other solution to remove CO2 emission, right? In that sense, I totally agree with Yogo-san in the sense that the CDR and the CCU should be only used for the case where there is no other substitutional technology. But for those, currently, we maliciously compare, for example, SAF and the existing fossil fuel, and the SAF is expensive, but that discussion is nonsense to me, because that is actually never considering the constraint of net zero. So if net zero constraint is the first priority, then we have no solution for the fossils, right, for the air aviation, or the substantial CDR to compensate for that emission upon the burning of the fossil fuel for aviation, for example. So in that sense, I think that if we prioritize, again, that net zero constraint, then we would converge to the very, wise portfolio of using the most suitable technology for the most suitable sector. So in that sense, the CDR may exist or should exist, and the CCU should exist just for the case where there is no other substitution. This is my consideration.
I'd like to offer another view, and that is that for many years, all of us have been very focused on what the IPCC worldwide models tell us that world governments need to do. And world governments are not acting fast enough. On the other hand, something that is completely absent from those models is what these local jurisdictions and businesses want to do in order to maintain their own net zero goals. And this is what's happening in the CDR market today. That's where the money has come from. That $10 billion that's in contract that hasn't been spent yet is coming from private companies who want to have their own net zero goal. And that's an entirely different focus than what we've had up to this point, and we need to pay attention to that. And what it's telling us is that for those people, this is an extraordinarily valuable commodity. And why is that? Because it's not pollution control, it's reputation. They're buying reputation. And so they're paying more. And eventually, as we get to a regulated market, we get to the point where everyone around the world is forced to do this, the price will have to come down, because there are lots of people who don't care about their reputation. They need to be forced. But today, that's not happening, and we need to take advantage of that and recognize that this is a different model than we learned about in the IPCC models.
Yeah, thank you. Thank you for those comments. I think this is a very important topic. I work at a university, and I've worked on carbon management, my whole career. And I can say it's often I hear from my colleagues that what I do, carbon management, carbon removal, is not needed. If only we would get along, fast enough with transition to renewables and so forth. So I think that this is an issue we need to continue to discuss, of why it's so important, and build the space so that this can be developed. I want to switch to really an entirely different topic. Governments around the world are, grappling with, their R&D investment portfolios, and there's always a choice. You can invest, everywhere from, TRL1 to 8 or whatever, and each of those levels of maturity, different strategies would favor one or the other. And CDR is very interesting in that there are technologies available that are being scaled up to the gigaton scale, to the million ton per year scale. Thinking of carbon engineering and the Oxy projects in the US. And we're seeing a lot of this come along. So one could say, well, gosh, maybe we have enough technology and we really should devote our efforts to maturing what's available and we know about. On the other hand, it's very early days. I think that the idea that we would need carbon dioxide removal, it was really only like a dozen years ago that this became clear that this was going to be necessary. So it's still such early days. So what I wanted to talk about is, what is the case for continuing to invest in basic research? And Professor Sugiyama, you talked about artificial photosynthesis, which is really very early days for technology, and fundamental research is required if we're going to be able to achieve this in a cost-effective way. So could you sort of help make the case for the need to continue to invest in fundamental research?
Yes, so thank you for this wonderful question. So the first my conception is that at least as a scientist and engineer, we community have to provide an answer to decarbonize each individual sector. So in that sense, as I have told you, the chemical product is quite essential, and that necessitates carbon source. So we can think about, or we have to think about how we can sustain that industry or the supply of the chemical virgin product, even though we circulate some recycling, still some necessity of the virgin chemical feedstock actually exists. And how to obtain that in the era of the carbon neutrality, then the solution might be just from the CO2 in the atmosphere, or continue to use the fossil resources and offset that CO2 emission by CDR. So 2 solutions, largely speaking, I think. And the latter might be the issue of some, the final choice of the technology, but I think that at least we need to develop a technology to make our chemical industry to be sustainable. So that necessitates a kind of some artificial photosynthesis or the combined natural photosynthesis and some engineering, like biocarbon. So those technologies are still quite immature, I confess, but as I have said, if we never have those solutions, then we have to just rely on the CDR at the last stage. That might be possible, but as the technological choice, if that seems to be still available in a couple of decades later, then we should just focus on, still continue the good farming to cultivate those basic but promising technologies. This is my answer.
Okay, thank you. Would anyone else like to comment on the topic? Dr. Aines, you were an advisor to the Department of Energy. What advice were you giving them?
The need for innovation is continuous, and it's an ongoing thing. And I don't think we should be reducing the innovation investment that we're making or the kind of thing that we're doing here at ICEF. But the next stage also needs to be done in parallel, and that's something that we need to recognize, is that in so many discussions we seem to think that these things are serial. We're going to do A, then B, and then C, and that's not how it works. You do these things in parallel. Sometimes they don't work. We all see that in the newspaper, but sometimes they work amazingly well and they're going faster. And so it's important to have a lot of options on the table and recognize that you're going to pay for things that you might not use, and you're also going to you're going to get lucky. It's okay to get lucky, but we have to have a lot of options on the table. But we also have to recognize that we have to grow these things. Boy, Marcus, when did I meet you? 13 years ago? Yep. It's a long slog to turn something like that into a business, and we have to pay attention to the fact that we don't move 1 billion tons of anything without businesses that make money doing it. We need to help those businesses grow.
I just want to make a remark. When's the best time to plant a tree? 20 years ago. And equally with technology, climate technology, as I said, 20 years or more. The Nobel Prize has just been awarded to a significant technology in carbon capture called metal organic frameworks, MOFs, from Japanese, Australian and US researchers. They started that in '89. That's how long ago these technologies, took and are taking to develop. We are running out of time. Therefore, the R&D expenditures, but also getting to what we call first of a kind. So the plant I showed you, Myrtle, that's a first of a kind in industry for our technology. These take a lot of capital, these take a lot of time, but we also need climate capital, and that's something that hasn't really emerged for us. And that is a separate type of capital that isn't bound up into the capital of the world in the GDPs. This is actually defined and ascribed to accelerating our technologies, and we are calling on the world, many of us, and also in all the different forums on bringing that new capital to bear, and that is actually backed by government. Government has to accept that it is the investor or the investor of first resort. It's the first one to put money on the table, and it's also the insurer of last resort, because if we fail with climate adaptation and we fail with meeting our climate targets, we all fail, and that's where governments really have to step up.
Okay, just before you start, this is your warning. After this next round of questions, we'll turn to the audience. So yeah, start getting ready, and please go ahead.
Yeah, no, I was just going to pick up on a couple of points that were made earlier. And in fact, Roger, you know, in your presentation, you said there were interesting numbers, 790 companies that are involved with CDR. And you had said that this is an umbrella of technologies. I presume some technologies are focused on locking down CO2 permanently through mineralization. Others result in, you know, the creation of fuels that then emit CO2. So would I be correct in sort of implying that those 790 companies, Roger, that you've talked about, are in fact focused across the spectrum of technologies? And if indeed that's correct, is there some way by which you could tell us what are the drawbacks of some technologies vis-a-vis other technologies, especially those technologies that, you know, lock away CO2 permanently versus those that actually generate or result in the generation of more CO2? Is there some way by which we can actually assess or evaluate the benefits and drawbacks of these various technologies?
Those 790 were, in fact, only ones that remove from the air and with the intent of making it permanent. Their permanence is in question, but it's not utilization. That's an entirely different set of companies. I think that the metric that we have to apply here is acceptability. Again, are we happy with these things? Do we want to make our jet fuel from CO2 and electrolysis hydrogen? Or do we want to make it continue making it from petroleum and offset it with direct air capture? Both of those are entirely reasonable outcomes that we don't know yet what the public is going to accept. And we simply have to build both of them up to the point that we're able to really discuss it. This experimental phase that we're in, where we just try things out and then pay attention to what people think about it, because trying to force fit things into the public, we've found, is not a great idea. So, but I'm not sure if that answers your question, but
that sort of, yeah. In a sense, I'm getting a sense that the 790 companies are focused entirely on one technology, which is to permanently lock away.
Yes, those are direct air capture, BECCS, ocean, soil.
But is there some way by which we can, in fact, decide that those technologies, the 790 companies, should be granted greater support by the government because they result in the permanent, sort of lock away of CO2? Should the government be promoting those companies even more aggressively than they are now?
Yes.
Should the market be promoting them more aggressively?
But I think you're asking it by comparison to utilization, by comparison to making products.
By comparison.
And we do not know that answer yet. We have to do them both.
So we do have to do them both?
Absolutely. We need everything we've got, and then we need more. This is a very hard problem. I think you all know that.
May I append quickly one thing? So for that, two choices of the perpetually, capturing the CO2 into somewhere and never allow the CO2 to come again to the air, or utilization, which actually just make a route of the circulation of the carbon. So the latter, CCU, definitely necessitates a substantial energy for converting the CO2 to the active form, which is the hydrocarbon. So that actually quite energy intensive from the theory, from the principle, compared to the most of the case of just embedding the CO2 into somewhere. But on the other hand, disposing the CO2 somewhere always necessitates some good reservoir. So how much is that capacity of the reservoir? That is always a problem. So that means that we never have, in my opinion, some Superman, right, to solve everything. So some portion is strong, but some portion is weak, and vice versa. So that's why I think that we need to still seek for two possible ways, and inside of those, we have some multiple options inside. So we need to think about always some portfolio of the technologies, which are very high TRL and low TRL, but the low TRL never means that is desperate. So we need to be more familiar with what's going on inside.
Michael, you have a view on this?
So portfolio approach is the only approach. We really need all solutions. We need to validate them, and that's why TRL was actually developed, to bring standards. So we need cooperation, collaboration, we need standards, we need interoperability, we need these, we need hubs to emerge for CO2 utilization, which will have DAC, which will have some industrial capture, because at the end state, we can take all that CO2, through our process and many other types of processes as well to end up into permanent storage, but also maybe fuels and other types of semi-permanent or carbon loop. So, I mean, significantly, our first customer is the biggest producer of bricks for the cement and steel industry, high temperature bricks. Their emissions come from heating up and making those bricks. You can't get it from substituting to renewables or anything like that. We capture that CO2 in a cycle, and then we make the materials that they then heat up again. So it's actually in a cycle. So we can decarbonize a whole industry with our technology, for example, just one technology. And that's where our technology is very, very purposeful for that. We need many other technologies to actually be to be identified and to adapt for that particular industry. So industry pathways, as you said, are extremely important. This is, and there are many different technologies that will suit that industry pathway.
Okay, you, please.
My opinion almost says with Rogers and the others, we think that we should develop all potential technologies for large-scale application, and we should not rely on a single technology to such a large, such a big challenge. Each technology has its own advantages and disadvantages. And for example, the DAC with geological storage is one of the most important CDR technologies due to its immediate impact and quantitative potential and low reversal risk. However, it is not clear to what extent DAC can be scaled up at this moment. As you know, the recently reported, the climax has not yet been able to capture 1,000 tons of carbon dioxide per year. So, as far as I know, the engineering-based DAC, there is almost no plants, only 1 or 2 plants that can actually capture the carbon dioxide more than 1,000 tons per year. And I discussed with the director of the carbon engineering 2 days ago, and 1.5 the Storas project will soon operational, and it will capture 500,000 tons of carbon 500,000 tons of carbon dioxide in this year. They said that. But so I'm looking forward to see the results of the Storas. And so my opinion is that we should develop all potential technologies.
Yeah, it's definitely very early days. Okay, as promised, questions. Okay, please. And I believe someone will bring you a microphone.
Thank you very much. I'm quite intrigued that in all we've been discussing, we did not discuss what I think is by far the most important and most nearly accessible technology, which is to transform the agricultural sector. You mentioned in your earlier comments, Sally, that 2 billion out of the 9 billion is from forests. Well, now we have new technologies that enable us to transform this. We could have the trees that are growing to absorb twice as much CO2 as they used to in their conventional form. We now can design crops that have the traits of being heat resistant, salt resistant, have deep roots, etc., etc. We can even perhaps dream of having the C3, C4 pathways of plants transformed and getting nitrogen fixation out of the legumes and into the cereals as well to reduce the need for ammonia and fertilizer. Most importantly, the experience that was done in India in the 1960s, as I mentioned, transformed India. And India was not a pilot project. It was 450 million people on a continent. And it transformed India from being an incredibly food deficit situation into quintupling its food production and covering 1,400,000,000 people and being a major exporter as well. Now, it can be done very quickly because once you have the seeds, every year you improve, the seeds can be spread, and therefore the transformations don't require major long-term investments. We have unfortunately turned back from our investment in agricultural research, which was driven initially back in the 60s by the Green Revolution and Norman Borlaug, who won the Nobel Prize for advancing that. We've moved away from all of that. We should come back, and this is a prime good carbon capture and sequestration, I believe, would be done. And more importantly, you get an incredible additional benefit. Our SDGs 1 and 2, poverty reduction and food security, is largely through dealing with livelihoods of the very small farmers throughout the very poor part of the world. And that is best done by the transformation of their agricultural systems. So I think that this is a priority. We can turn the agricultural research with what we're doing now in the new biology, what we're doing now with AI, what we're doing with communications. And if they could do it with the communication and infrastructure and science of the 1960s for the scale of India, we can do it with our 21st century technology, communication, and infrastructure for the whole world.
Yeah, thank you. I think you just joined the panel and, and offered another perspective. Would anyone like to offer an opinion about the state of agricultural research and the role of modifying agricultural practices?
So may I give you a quick comment? So I fully agree with the necessity of engineering the bio, right, to make them grow faster, to give us more food, or to give us more sugar, to be a source of, for example, the bioethanol. So these are significantly important technology and probably can be quicker than the case of our electrochemical technology in some sense. But let's think about the case of the sugarcane, for example. The sugarcane gives us the, say, sugar. But also, there is still the remaining huge amount of the, say, biomass there, other than the sugar content. That can be also used for the, for example, the source of the power generation, or in some cases, converted to other chemical product. So my point is that not only just focusing on one sector, which is necessitating the more sophisticated bioengineering, but also coupling among the different technologies. In some cases, such a nice combination between the bio and also some inorganic catalytic technology or electrochemical technology may give us a very nice how to say, the plant technology, which can utilize our energy in more efficient manner. So that would be some good outcome or the byproduct of the individual technological development. This is my opinion. Thank you.
Okay, thank you. I think we need to wrap up. So sadly, we can't ask the rest of you to comment. But would you like to go ahead?
Well, thank you. I mean, I found this panel discussion very interesting. I mean, as I said, I'm an economist and not a technocrat, so I learned a great deal. But, I mean, it's clear to me that the technologies that we're talking about, whether it's for carbon removal directly or whether it's for utilization, are absolutely essential going forward. But the point you made, Roger, which I thought was interesting, was that this has to be now not a sequential, not a serialized sort of progress. It has to be done in parallel. And we must move forward along all fronts. And that, I think, is a very important point. It's clear that we have challenges, major challenges. I mean, supply chain issues were raised. You've, in your presentation, talked about cost reduction. Everyone, actually, in some form or the other, talked about the importance of bringing down costs. But I also sort of picked up that we're absolutely critical that we have systems that are simple, that we focus on modularized, simple solutions so that the bridge or the gap between a technological pilot project and its implementation and then its implementation to scale is successfully accomplished, and we do it within a time scale that's realistic. We are running out of time, as someone said, And we know that. And therefore, whatever we do today, I think we have to do it with everyone, with all hands on the till. And that means government, business, researchers, laboratories, people like us in this room, all of us, we have to actually get to the task. And the final point I picked up, Sally, was that there is an issue with regard to the public. We have to recognize the public needs to be made more aware of the importance of these technologies. It's a public good now. Heightened public awareness is critical. I don't think people understand how important this particular initiative is. So that's my sort of large points. I mean, thank you very much, all four of you, for enlightening me.
Just adding a few more thoughts. You know, we're at the very, very early stages of the idea that we're going to manage carbon in the environment. And I think the suite of technologies that we are discussing here and the many that we didn't get to talk about here are going to, over the next 100 years, allow us to restore the atmosphere to a level where we no longer are worried about global warming. But I think it's also more important than that. It will also put us on an important path towards true circularity in all aspects of our economy, and that the carbon atom, or the carbon element, is a very valuable element in our society, and we're going to need to figure out how to use it. So circularity around carbon, I think, is going to be a very important technology. So I like to think if we look back on our meeting here today, 100 years from now, we'd go, yeah, thank goodness that these people were thinking about this and innovating, and governments were investing, and people were supporting these technologies. So thank you very much to our panelists. We're seeing into the future.
Thank you, Professor Benson, Mr. Mita, and all the speakers. So this concludes CDR and utilization session. So I would like to send our speaker and our moderator with a big round of applause. Thank you very much. All right, please proceed. Thank you.